叫石健，是那个 Kornia 的 co-founder。然后今天我给一个 talk about the accessible agentic computer vision with Kornia, as more precisely it's an introduction of Kiwi. And let me. Yeah. So what? Oh. So first, let me introduce what is Kornia. So you may think Kornia as an OpenCV, but written in PyTorch. So we provide all the computer vision operators as PyTorch within the PyTorch framework, and you can think every computer vision operators as neural networks. So by supporting this feature, so it will allow you to have GPU accelerations, and also with batch image processing, which is now really supported by OpenCV by now, and which can provide you a faster inference speed and image processing speed. And alternatively, if you are chasing for a very fast performance, you can also convert all your computer vision operators to Onyx, or even for TensorRT. So, and if you want, you can convert any computer vision operators to any processing unit, as long as the PyTorch is supported, such as the OpenVINO. So you can do the OpenVINO conversion without any further conversion coding there. And so another important feature we provide with the Kornia is the differentiable operators. So we put all the computer vision operators as neural networks. So each operators can be differentiable in terms of it allows you to flow the gradient from your computer vision operators, from your computer vision operators to neural networks, or to the neural networks to the computer vision operators. So it allows you to have a trainable computer vision operators in here. So in general, Kornia is widely adopted worldwide. So we have above 10,000 GitHub stars, and with more than 2 million downloads per month. We are closely collaborate with multiple collaborators, including open source collaborators with open source libraries, and also with some other research institutions. Well, Kornia is more or less designed for research and development purposes. It's not really ideal or optimized for inference and deployment. So to better support such inference and deployment speed to make it faster, well, for the real world use cases, we also introduced Kornia Rust. So we use Rust here for two reasons, majorly for the memory safety and for the performance. So apart from, so unlike C++, so with Rust, we can achieve the C++ level of speed, but without those headaches such as you need to garbage collection and some memory bugs. So in general, we have four features for the Kornia Rust. We have memory safety, the performance, and also the cross-platform support and the real-time processing. And compare with other Rust-based image processing libraries, Kornia Rust can in general offer a 3 times to 5 times faster performance. And we have recently released a technical report on our archive. So if you are interested in the details, you may check it out. Anything else? Yeah, so and also we are involved in the Google Summer of Code this year. So we have 2 interns, and one is working on robotic applications. So it's working on the April tag detection, and another intern is working on a Rust-based implementation of a vision language model, which allows using Smallville and them. So in general, Kornia Rust is a very important project to us to step into the world of embedded AI. So it allows us to explore more into the robotics, mobile, and edge computing, and wherever the areas that requires a millisecond performance there. So, well, both Kornia and the Kornia Rust libraries are low-level libraries. So they provide low-level computer vision operators and low-level, just a low-level computer operators. It does not, it will always require you to have some domain knowledge of computer vision, and requires you with a familiarity with library API. So it's not really user-friendly in such a sense. That's why we are now building Kiwi here. So Kiwi is a agentic computer vision system that based on the recent success of large language models. So it's more a user and the tooling system that can automatically build the pipeline or computer vision pipelines without any coding experience, without any domain knowledge of what APIs or what functions you are going to call. So one typical example is daily vision chores. So as a developer or researcher, what you daily must be doing is you must have a lot of one-off scripts here. What we call one-off scripts is it's very simple, it's not very hard to build, but it's very annoying, such as you may need to resize the images within one folder. Like you have one folder of images, but you want to standardize it to 512 by 512. But in that case, you will mostly do it by once, and you like, for example, you right-click on your editor and create a new file, name it tmp.py, and you create a temporary file, and you generate the code from the large language models, or you write it by yourself, and then you may, if you encounters any bugs, you want to debug and run it. Most importantly, you may forget about the file later, or just delete the file. So you may not really able to carry this file to your next project for your new experiment. So this we call one-off script is kind of annoying, not in terms of its time inefficiency or it's not it's a difficulty, but it's mostly can break your chain of thought. So you're thinking at a high level. You're thinking a new experiment. What are we going to do? Well, I'm going to do a new fancy project. But after you realize you need to this just a simple, stupid resizing, you pose your thinking and down to a stupid work, and after that you need to come back to the thinking. That's a bit frustrating, isn't it? So that's why we introduced Kiwi here. So Kiwi is more or less the agentic computer vision tool, but it's just purely based on natural language. It's like here, for the previous agentic, for the previous resizing example. So you can just tell Kiwi that within terminal, you can say, okay, Kiwi, resize images and the photos to 512 by 512 and save it into resize the folder. So it will understand your query and create a pipeline that includes, okay, where are the images I need to read and what operations I need to operate. Just operate, and where to save all the images. Yeah. So within the pipeline, so you're more or less just focus on what you're going to do, but you don't need to think even on how, or even for the simple pipelines and image I/O operations or the simple resizing. So alternatively, just similar to any other large language models, we support a interactive dialogue. So what we call the conversational AI nowadays. So for example, you have sudden thoughts like, okay, I want to reset all the images under the photos folder to 512 by 512. And Kiwi will come back with a response that, okay, I'll reset all the images and the photos to 512 by 512 using bilinear interpolation, and saving the results to the output folder. But here we got 2 points. You didn't think in your first thought. So okay, you just realized, no, I don't want to use bilinear interpolation. I want to use bicubic interpolation instead, and I want to save it. Instead of the output folder, I want to name the folder as reset. So you come back with Kiwi with a new prompt that okay, I want to use bicubic interpolation, and I want to save it to reset the folder. And then Kiwi will confirm back, comes back with a new plan that, okay, I'll do whatever you want, and if you are like it, it's just to confirm, and Kiwi will proceed to the plan and to do whatever you want. So we designed Kiwi for 2 major purposes. One is for a simple conversion task as a previous design. So like we have like a simple image geometry transformation, or if you are working on some maybe your artist working on generative models, you may want to do some edge detection from your images as a signal or something, or you can do a simple image enhancement, to adjust the brightness and contrast. This is simple thing, so you don't need to do it by yourself. Just use the Kiwi, just give the command what you want. And another interesting demo that we're working on is that we are working on embedded AI demonstrations. So, which is we integrate Kiwi with a robotic arm, which allows the Kiwi to read from the camera input and generate the pipeline and return with the actual actuation. So simple commands like Kiwi just detects the object and grabs the apple for me. So in that case, the Kiwi will read from the camera inputs, and instead of the previous example that we are saving the new image or new output to a file, but here so we don't return a file, we just return it as an actuation back to whatever the robot you're working with. So this is one, just to give us some demo about how the things exactly working. So Kiwi with the 3 steps of work is with every query you're inputting ways. So we have the planning stage, execution stage, and the outputting stage. So with the planning stage, for example, with the resize example, so with this planning, so it will have 3 steps. So the first one is will know which folder is to read the image and what operation I need to perform with, and also what are the output folder and what are the output format I need to deal with. So after understanding this, and with your confirmation, and you will do the execution accordingly, and you may check out the results later after all these procedures. So another demo is a metric computation. Like here is a way. So sometimes you are a researcher, or you may want to report some numbers like SSM or FID between 2 folders, but you may not need to necessarily write every code by yourself. Here by the planning stage. So we have after you give the queries, it comes back with 4 steps. We're gonna read images from the first image folder, and another bunch of images within the next image folder, and it will run the operation with SSM compare, and then decided with CSV output, and instead of saving as another images. So it will, after your confirmation, it will run everything as planned there. So our whole system designed with a whole total 5 steps. So with query processing, and it will generate a execution graph. With the execution graph here, basically means two-chain graph, a pipeline that with all the functions you will be running with, and also with the data planning. So it's confirms with what are the input, what are the output, and the execution is determined. So depends on your planned data. If your output, what are the output? If the outputs are images or videos, or the outputs are just terminal outputs or standard output of CSV file, or the actuations, anything, and it will handle the output accordingly. Right, so this is kind of details I may want to skip later, but it's just for example, so the whole Kiwi is based on the MCP schemas, so it's on the JSON file. So for each function you're providing, so we just create an MCP input schema, and with here I noted here we have additional 2 nodes fields and the node ID fields that is basically used to construct the graph later. And okay, here's the output. So we also, let's just skip this, but we also support different triage. So we have if you have a parallel process, we can also do that with it. So this is one important thing that we want to mention. So the whole KV is based on the graph representation. So we have, apart from the first input nodes and the last output nodes, or every nodes in between represents an operation. So the operation, basically all the operations together builds up with a pipeline. So with what we call here is we call a forward declaration node system. Is we build the graph with one call from the large language models directly. So with the previous mentioned, we have the 2 nodes. So if for each, like from here, the example, the first node will know what is the next node to go to, and it will know the node ID for the next node, etc., etc. So basically, we call the whole graph in one call. We don't need to do the repeated large language model calls. So, and one strong benefit for such design is your data will always belong to yourself. So we do not need to upload any images or videos onto large language models like GPT files, to the GPT cloud or etc. So you always keep your files locally, and what you only need to do, so from the Kiwi, you may send the query to GPT server only, and after the server returns with a pipeline and with generated pipeline, so every computation will be executed locally. So so your data is safe by yourself, safe for yourself. Right. So this is a demonstration. But basically, like some other agentic computer vision tools that will need to upload all your images or videos onto the cloud server. So if you have 10,000 images, okay, you will upload 10,000 images. So that means lots of money you need to spend with it. And also, apart from the uncertainty of the large language model may shake a little bit of your request. So it's the money cost is very expensive. But with Kiwi here, so we only need to upload your prompt plan, your query onto the cloud server. So how many images you are proceed with, so you only need to pay once, whether with merely 200 tokens. If 200 tokens is quite a lot here, we assume. So you have iterative planning with the Kiwi, total Kiwi there. Right, and also if you are working in a very strict environment that you do not even allow to upload your queries onto the cloud server, so we also support the local OLAMA. So if you have a local OLAMA deployed in your local computer, your local cluster, you may just configure Kiwi to directly call to the local OLAMA in that case. So so even for both the query and your data will stay inside your server and your system, so you do not need to upload anything at all onto the server. So this provides a better stability, but okay, one thing to mention though, I didn't try much with the local OLAMA, so I tried with the Queen 7B or something. It's not a very big model. Sometimes it can collapse. I think with small large language models, it may be collapsed with some bad outputs that may not that we do not interpret it well. So, but I didn't try. I don't have a strong machine by hand. So if you have a strong machine, you may try a HANGZHOU model. I think probably it will work very smoothly. So the next part is a data planner and execution selector is also some technical details there. But basically the data planner is to give a plan of the data I/O mapping. So what are the input, what are the output, like here, so we have photos. So what are the input photo, what are the output photo names, to just give a naming strategy. And if you are CSV file, to where the CSV file, something like that. And the execution selector to do the same. So if you are saving your output as an image, so you can save it as an image file, or if it's a CSV file, you save the CSV file. If you are actuator, so we put it back to the, we save the actuator file, whatever you want. So, right, so one other important feature that we have is we have Graph I/O service, should be save and reusability here. So we support you can, for example, you have built for example, the previous resizing example. So you're using bilinear interpolation to do your resizing, but maybe the other day, so you realize usually it's bicubic. But in that case, if you do not want to run the whole process again, you may just you may save the whole pipeline and alter the configuration by yourself. We will be saving both the graph JSON file and data JSON file into your local disk, and you can all of them can be used for reuse purposes, for the reproducibility, and if you can for debug purposes as well. And Also, if you can say, if you have a new graph file, you have your old graph file, but you want to run on a new folder, you can just run something Kiwi, just run it on the new photos folder, and to do the same execution file with mypipeline.graph.json, so you can do them easily. So first summarization of this whole system is we have 3 sections. So first is the natural language query. So we handle the natural language query with corresponding what tools and functions we'll be using. And then I should not put as an OpenAI graph planner. So at the planner stages, we have 2 planners for the execution graph plan and to the data plan. And after that, so we have all the tools we'll be using and all the data we'll be using, and then we have the executor we'll be using, so everything will just execute as you requested. So to summarize, all core features for Kiwi includes, basically we have a natural language support to execute all your computer vision tasks with a level of privacy preserving architecture. And also we'll be supporting embodied AI to work with different cameras and robots and for various perception tasks, etc. And also we have a higher scalability that on top of, currently it's just on top of Kornia, so you can use GPU accelerations to do all your things, or if based on Rust, you may do the cross-platform execution, and also later on we'll support more large language model backends like others. So the general goal for this project is we want to democratizing the computer vision to lower down the technical barriers to everybody. If you are really advanced researchers and developers, we would like to free you from some daily stupid tasks. You may use it directly to ease your work, to concentrate on things that are important. So if you are a junior person that you do not really familiar with everything, but you're an artist, you want to use the Kornia as a preprocessor for your images and to generate beautiful images or videos, you may use it. We provide the natural language exercise that you can use it easily for your artists, for your arts. So in terms of roadmap, so our near-term roadmap includes we want to add more features. We want to add more large language model support with different like Cloud, Gemini, or Mixtra, and also we want to add more tools like FID or RPIPS computation, etc. So and with the midterm, so we would like to focus more on the Rust side, a better Kornia Rust integration, and with better more demos with embodied AI and robotics. And also, we would like to add more tools for some domain-specific functions, such as if you're dealing with medical images or you're dealing with the remote sensing images. So those function tools should be very different from your common tools like we already done here. So. And alternatively, so what we want to do is we want to have a very generic agentic computer vision tool stack for the autonomous AI system and to do everything to every simple task that we'll be doing. So I don't expect this to be replace the developers and to do very complicated tasks that I will assume it can do the code for you for for simple tasks less than 100 lines of code. And we will do more optimizations for the edge devices and edge devices and for robotics, so we make it faster in the final version. Right, so we call for collaboration here. So if you are interested in this project, you may feel free to join our community, and you may just jump into the Kornia's webpage to join our community. And if you are interested, you may contribute to Kiwi as well. And we are also seeking for partnership. So if you are interested in the project, you have specific needs, I think we can do it together. So feel free to contact us. I think that's conclude my work, my presentation, and thank you much.